So section 4.2, null space, column space, and also if we have time, we'll be talking about linear transformation as well as kernel. Okay, so these are the main concept that we'll be talking about: null space, column space. I think linear transformation we already discussed in our last chapter. And if we have time, we quickly recall those properties and do one or two problems just for fun. And another important concept is kernel. So basically, these three concepts that we'll be focusing. Now, first of all, what is null space? Okay, here is the definition. The null space of an M by N matrix A, written as Null A, is the set of all solutions of the homogeneous equation AX equals 0. In set notation, we write the null space as null A equals all X, all the objects from Rn, because remember, this is a set, matrix A has M by N. The size of the matrix A is M by N. Therefore, this X is a X belongs to Rn. If this is 2, then that will be R2. If this is N is 3, this will be 3, and AX equal to 0. Just by looking at the definition, it may not make sense to some of you. That's okay, don't worry. So we're gonna do this with an example, and hopefully it will make sense. Now let's look at this example. Example 1. Let A is a matrix given here, and we are given a vector U. Now we want to check whether U belongs to the null space of A. So how do we check it? Well, by definition, what you do is, according to this definition, you just find AU. Okay, multiply. A is a matrix. It's like a function. It's like a transformation. So you do this AU. Okay, multiply them, and if you get 0, then it is in the null space. If it is not 0, it is not in the null space. Okay, that's it. Let's look at that. AU 1, -2, 2, -1, 2, -3, -4, and 5, 2, 1. And I want you to multiply this and let me know whether you get 0, 0 or not. So I believe you're going to get 0, 0 here. I did this mentally quickly, and then that turns out to be 0, 0. And so, yes, U belongs to null space of A. So what it means is, if you think this matrix A as a function, then what we did is, in function, recall from your high school, you have a domain, and then you have a range here, and there is a function, and suppose in the domain, and function is, let's say, x squared, for example. So if you have x equals 1, and here you will get 1 squared, which is 1. And if you have x equals 2, then this will be 4, and so on, right? So that's what the function does. Same way, we have a object x, or U in this case, for that matter, U is a vector in the domain, and there is matrix A, and if we multiply that, and it gives 0. Here we have all this different one, but in order for this to be null space, then every element in the domain, when you multiply with A, must give 0, and the set of this is called the null space. Okay, the space generated by those vectors here is called the null space of A, whatever is there, because everything when you multiply with A gives you 0. Okay, one very important observation here. What is the size of A, which is 2 by 3, because there are 2 rows and 3 columns. Okay, size of this matrix A is 2 by 3. And you see the U vector, which is 5, 2, 1, actually belongs to R3, because there are 3 entries. So U belongs to R3. So that means, you know, the null space of A, suppose if I take a matrix M by N, for example, then null space of A is actually the subset of, null space of A belongs to R N, for if N A is M by N. If this one is 3, then here is 3. See that, that null is, the object here, the null space belongs to R3. If I consider my matrix to be M by N, then the null space will be Rn, not Rn, not Rm. Just keep that in mind. So the second one, the row, determines the null space. All right. Now let's look at theorem 2. The null space of an M by N matrix A is a subspace of Rn. This is exactly what we just discussed. Okay. So if the matrix A is M by N, then the null space of A is the subspace of Rn. All that you need to know. Now, let's look at another example. Find a spanning set for the null space of the matrix. Sometimes these questions may be given to you as find an explicit description of null space of A. Okay, it means the same thing. So in the exam, don't get confused. Sometimes, people messed up because they think that the question is telling to do something else. Well, that's why, language is very important in linear algebra. Unlike your calculus course where there are lots of formulas that you can apply, here you need to understand the definition and theorem, and then use those definition and theorem to solve the problem. So it requires a lot of reading compared to other math courses. Just keep that in mind. Now, in this example, we need to find a spanning set, or you can say that we need to find the explicit description of null space of A. Now, what does that mean? How do we do that? Well, remember, by definition, as you can see, null space means AX equal to 0, right? So that's the definition. We need to find X such that AX equal to 0. That's all we need to find. By definition, null space means if X will be in the null space, okay, X will be in the null space if AX equal to 0. So that's the definition. From now onwards, I'm not going to put that vector sign here, even though, because sometimes when we talk about the matrix, then the matrix does not, like, we notice that even, let's say, if we have A, let's say 1, 0, 2, 3, for example, we can consider this as a vector if it satisfies those 10 conditions, right? So we define the vectors in a much more broader way. So from now onwards, I'm not going to write that arrow sign because it does not quite fit with the narrow definition that you learn in high school. Vector means, some direction and magnitude. So we define vector in a much more broader way. Anyway, so that's what we need to do. All right, so let me just write it down. AX equal to 0. So A is already given there. -3, 6, -1, 1, -7, and 1, -2, 2, 3, -1, 2, -4, 5, 8, -4, and X will be, you know, X will be, now you have XC. In order for this matrix to exist, or you can think this way, this is actually M by N matrix. That means we have 3 by 1, 2, 3, 4, 5. 3 by 5. So we know that null space X, if X is in null space, we suppose that X is in null space, then X must be a subspace of R5. So that means we'll have X1, X2, X3, X4, X5. As a matter of fact, for this matrix, the multiplication to exist, it must be of from R5, right? So equal to 0, 0, 0, 0, 0. Now, see, what will be this one? Can you think of this? This is 3 by 5.
3
And
by
this,
1.
yes, 3 by 1. That will be 0, 0, 0. All we need to do. Now, we need to find these values, okay? So what we do is now we consider the augmented matrix. You know, you can find those linear equation, but you don't have to, because we already know how to solve the system. All we need to do is just solve the system, okay? To solve the system, consider the augmented matrix. Okay, augmented matrix. So augmented matrix will be, as you know, that -3, 6, -1, 1, -7, 1, -2, 2, 3, -1, 2, -4, 5, 8, -4, and then, sorry, then 0, 0, 0. Now change it into echelon form, please. Change to echelon form. So I trust that all of you are, know how to change it into echelon form. I think the easiest one would be, let me just do one step, and then what I did here is that I switch R1 and R2, interchange the row, and then, and guys, I trust you, and I just let me know what is the last, I leave it to you. So blah, blah, blah. So, and then the final answer would be, okay, guys, my calculator tells me that the echelon form is -1, -2, 2, 3, -1, and then that's going to be 0, 0, 1, 2, -2, and then all of them are 0. That's what I got. Again, echelon form is not unique. You may have a different number there, but that's okay. Not a big deal. And I trust you guys that you are able to do it. Now find the general solutions, okay? So let us find general solution. And so the general solution will be, you know that this is x1, x2, x3, x4, x5. So you have x1 minus 2x2 plus 2x3 plus 3x4 minus x5 equals 0. Another is x3 plus 2x4 minus 2x5 equals 0, and another is 0, all 0. So, and then the basic variable is, as you see, this one is the pivot, x1 is the basic variable, and then in this one is the pivot, x3 is the basic variable. So the free variables are x2, x4, x5 are free. Okay. All right, now we need to express the basic variable in terms of free variable. So that means basic variable is x3. Let me just find x3 here, which is negative 2x4 plus 2x5. And if I substitute the value here, I'm gonna get, now I need to find x1 there. X1, just calculate, I trust you guys, and then your final x1 will be, after calculation, the final one. I'll wait for you guys, let me know. Okay, so if we solve it for x1, then we got x1 equals 2x2 plus x4 minus 3x5. Now we express the basic variable. The basic variables are x1 and x3. We express them in terms of free variable. Therefore, our general solution can be written as x equals x1, x2, x3, x4, x5 equals, x1 means 2x2 plus x4 minus 3x5. X2 is free. I just write x2. X3 is negative 2x4 plus 2x5. And x4 is free. And x5 is also free. So that means now you can write it down as x2, and then you split them, plus x3, not x3, x4, sorry, x4, and then we have x5. All you need to do is just figure out the vectors here. So x2, then that will be 2 here, as you can see, 2 and 1. There is no x2 in the third row, then that means 0, 0, 0. For x4, there is 1 in the first row and no x4 in the second, negative 2 in the third, 1 and 0. And x5, so there is negative 3 in the first row, and second row no x5, third row 2x5, fourth row no x5, and 1. Okay. That's what we got. Now, so what we are supposed to do here is, let me go back to the question and what we are supposed to do. Okay, find the explicit description of Null A, or find the spanning set. Okay, spanning set for the Null space. All right, so what we saw is that therefore Null space of A is actually created by those vectors. So those vectors are 2, 1, 0, 0, 0. Another vector is 1, 0, negative 2, 1, 0. And another is negative 3, 0, 2, 0, 1. So this is the spanning. Oh, I forgot to write the word span. Okay, you need to write that null space of A equals span of this. Okay, so the spanning set for the null space is given by this. Or if you want to write this in a short, let's say this is U, this is V, and this is W, for example, then you can write equals span of U, V, and W. That's it. All right, so this is sometimes called explicit description of null A, or sometimes you can just say that spanning set for the null space. That means if we are given these vectors U, V, W, then we can create that null space. Okay, we can create a space and with some linear combination. Remember, span means, you know, linear combination of these vectors will always produce A times whatever that linear combination will give you 0. So that's the null space. All right. Now I want you to observe one very important property. Okay, so this property is, you see all these U belongs to R1, 2, 3, 4, 5, R5, right? V also belongs to R5. W also belongs to R5. So that means, and the combination of this U, V, W also belongs to R5. So that means null space is actually the subspace of R5. That's what we can write. Now let's go back to the matrix. So the matrix is 3 by 5, and so the null space of A is actually the subspace of R5. Okay, R5, not R3. Just keep that in mind. We're going to use that concept later. Okay, that's all about null space. Now let's talk about column space, the second important concept here. So for column space, we simply write COLA. This means column space. Like null space means you just write null A. That means null space. It means null space of A. In short, we just write null A. In the same way, column space of A, in short, we write column A, but actually it means it reads as column space of matrix A. So what is that? Here is the definition. The column space of an M by N matrix A, written as column A, is the set of all linear combination of the column of A. If A has column A1, A2, AN, then column space of A is actually the span. Span means create, you know that. It's a space created by those vectors in column space of A. For example, suppose, let's say A is 2, 3, 5, 7, 1, 0, for example. Okay. So then column space of A is actually a span of this 2, 3, 5, 7, 1, 0. That's it. It means any space created by some linear combination of the columns of A is called the column space. All right, so that's it. So column space of A is a container whose objects are created by some linear combination of those vectors. What are those vectors? Those vectors are actually vector in the column of A. That's it. Now let's look at example 3. Find a matrix A so that W is in column space of A, where W equals this is given here. Okay. What we need to do is we need to find the vectors from this one. What are the vectors that created this space, W space W? Okay, that's all we need to find. So let us suppose that X is in W, for example. Okay, then X can be written as 2A minus B, 3B, A plus B, right? Okay, and so any objects which is in the container W, in the space W, then that must be of this form. So I can write this as this one is 2, 0, and 1. And if I take B there, so I'm going to get -1, 3, and 1. So W is the space created by or generated by these two vectors. What are those two vectors? 2, 0, 1 and -1, 3, 1. That's it. So now we need to find the matrix A. What is the matrix A? So these are the column of the matrix by definition, remember? So look at here. If matrix A is this, then the column space of A is the span of those vectors from the column of matrix A. If we know that those vectors, then so the matrix A is, so matrix A is actually 2, 0, 1, -1, 3, 1. That's it. So example 4, consider the matrix A. Okay, matrix A is given. Now what we want to do is we want to find column space. Oh, by the way, before I do this, now let me remind you one thing. Okay, so what we said is that suppose matrix A is given, and this matrix, this particular matrix is of 2 by 3 size. All right, size is 2 by 3. And what we said earlier in case of null space is that null space of A must be the subspace of R3. That's what we said. Now let us look at what is the column space here. So column space of A is the subspace. Look at the vector U, V, W. So this U 2 and 3, this belongs to R2, not in R3. So therefore column space of A is the subspace of R2. Okay, see that. It goes there, this 2 here, and 3 is the null space. Just keep that in mind. So if we are given a matrix A, for example, of size m by n, then what we know is that null space of A must be the subspace of Rn, and column space of A must be the subspace of Rm. Just keep that in mind. With this, now we are able to, you will be able to solve this example. Consider the matrix A, which is of size 2 by 3, clearly. Oh, I think I choose the same example there. I think you can tell me right away now. Anyway, so think for a while and then let me know the answer, okay? All right, so example 4, you already answered that column space of A is k equals 2 in part A. In part B, if null A is a subspace of Rk, then what is the value of k? Then k equals 3. You already answered that. Great. Now let's look at example 5. So we are given matrix A. Okay, this A, there is a, okay, I forgot to type in that A. So A is the given matrix. And there are two vectors given, U and V. In part A, we need to determine if U is in null A. That's pretty simple. I think all of you know how to do it without any difficulty. Take few minutes and try to answer both of these questions, and then we'll discuss afterwards, okay? Just a couple of minutes I'll give you to think. In part A, okay, in part A, to determine whether U is in null A, all you need to do is just multiply A and U, okay? Just consider A and U. A is 2, 4, negative 2, 1, negative 2, negative 5, 7, 3, 3, 7, negative 8, and 6. And U is 3, negative 2, negative 1, and 0. If you multiply, do you get all 0? What is the product? So the product will be, let me see. So when I multiply them, I'm gonna get 0. I got 0, negative 3, and 3. So which is not equal to 0. Okay. So U is not, does not belong to null space of A. U does not belong to null space of A. It's that simple. Now the question, next question, could U belong to column A? Okay, could U? So U has 1, 2, 3, 4 entries, but A, column of A has only 3 entries, so it cannot be, okay, because U does not belong to column space of A, because column space of A is the, subspace of R. If this one is 3 by 4, so this is subspace of R3, where U is a subspace of R4. Okay, so it cannot belong to that. So it's that simple. So in the same way, you can do this part B, and I leave it to you guys. Looks like part B, I think in example 5, part B, I think we need to do it together. Okay, this one is a little bit different than part A. Let's work on it. Determine if B is in column A. So B is a subset of R3, and A, column of A also R3. So this may be a candidate. Okay, this may be a candidate, but we don't know yet. It just tells us if let's say if B is, like 1, 2, 3, 4, for example, in R4, we can directly say that yes, it cannot be. Okay, B cannot be be in column A, but now B has 3 entries. It's a subset, it's a subspace of R3, and column of A also is R subspace of R3. Therefore, this can be a candidate. But is it subspace? I mean, is B in column space of A? We don't know yet. Let's check. How do we check that? Well, let us consider since V is 3, -1, 3, which is a subspace of R3, and column of A has 3 entries. V is a candidate for column of A. So to check whether V is in column space of A, consider the augmented matrix and see whether the system will be consistent or inconsistent. That's all we need to check. Okay, so V is in column A. So consider the augmented matrix. A and V. Okay, which means A is 2, 4, -2, 1, and then -2, -5, 7, 3, 3, 7, -8, 6, and this will be, how did I copy the right thing here? Yeah, and what is V? V is 3, -1, 3, 3, -1, 3. Okay, now please change it into echelon form and see whether it is consistent or not. Okay, change to echelon form, and I trust that everybody know how to change it into echelon form. And so 2, -4, -2, 1, 3, -2, I mean this one will be okay. So let us take few minutes, and I want you to change it into echelon form, and then we will talk. Okay, this is what I got when I changed it into echelon form. I got 0, 1, -5, -4, and this one is -2, 0, 0, 0, 17, and 1. Okay, this is what I got. Now, clearly, this system is consistent because if we have, let's say 0 and some number here, let's say 0 and 5, for example, or 0 and 1, for example, in that case, we say that the system is inconsistent. But now we see that this system is consistent. We talk about this in chapter 1 in detail. So clearly, the system is consistent. So U is in, so V is in column space of A. Okay, that's what we need to do. So V is in column space of A. Okay, that first part is done. Now, what is the second part? Could V be in null space of A? Okay, so next question is, B does not belong to, cannot be in, what is the question again? Could V be in null A? No, V cannot be in null A because V is a subspace of R3 and null space of A is a subspace of R4, so it cannot be there.